is going to tell us about probing exoplanetary composition using white dwarf stars. And
You don't need to do anything.
I have to bring it up?
You don't need to do anything. It's on the screen. Look behind you.
Yes.
But you do need to let Laura know when the time's up because she can't see.
I'll tell you when you're at, try to give you a little bit advance notice here. So it's 12 minutes.
Perfect. I've got a timer as well. So, oh. Okay, am I good to go? Sorry, I can't hear anything.
Yes.
Thank you so much. Okay, well, there we go. Hi, I'm Laura Rogers. I've just come over to the US. I was at the University of Cambridge before, and now I'm at Noir Lab. I'm really sad not to be with you, but really grateful for all of the organisers for letting me present online. So I'm going to talk to you about probing exoplanetary composition using white dwarf stars. And none of the work would be possible without all of my wonderful collaborators who I've listed at the bottom of this slide. So firstly, I know lots of people are experts about stars, and my argument is a white dwarf is a star. So a white dwarf is a stellar remnant. It's the core of a low mass star that's left behind after stellar evolution. So they're incredibly dense. They have the mass of about 0.6 solar masses packed into the radius of the Earth. And this means they have really high surface gravities. And because of that, we should see just a pure, clean spectra when we look at a white dwarf. So here you can see a spectrum of Sirius B, which is the nearest white dwarf to us. And this is showing flux versus wavelength. And you can see that there's only these broad hydrogen features in the spectra. But actually, heavy elements have been observed in the atmospheres of about 30% of white dwarfs. So this implies that there has to be some kind of ongoing accretion from an external reservoir. And here you can see a spectrum of GD362, which is one of our favorite, what we call these polluted white dwarfs. So this is one of our favorite polluted white dwarfs. And this has lines of calcium and magnesium and silicon and iron on top of all of these hydrogen features that you could see before. So based on this spectra, it really is kind of like a know thy star thing. So based on the spectra, we're really able to reconstruct the composition of the planetary bodies that have been accreted onto all of these white dwarfs. And so we can actually infer this bulk composition. And from this periodic table, you can see all of the elements that have been discovered so far in polluted white dwarfs. And we tend to find that things are kind of dry and rocky with a bulk Earth-like composition. So I like to say that polluted white dwarfs are therefore mass spectrometers for exoplanets. So we're really able to work out the bulk composition, the bulk elemental composition of the bodies that have been accreted onto these white dwarfs. And a big aim in our field is to actually increase the number of exoplanetary bodies that have really well measured bulk compositions. And this is so we can really get to the point of statistical samples. So I'm going to talk a little bit about two papers that came out last year, where we added 7 white dwarfs to the literature with well-studied abundances. So I'm going to show you a couple of plots like this, just to break down the plot first. So this is a plot showing element X normalized to silicon, and then also normalized to solar. And X is an element across the X-axis. And they're ordered in increasing volatility or decreasing condensation temperature. And so when I put the white dwarfs, the data points from the white dwarfs on here, if you had abundance ratios that went straight across at 0, you would be accreting something that's very primitive and with a solar-like composition. So you'd probably be looking at something quite icy, maybe Kuiper belt-like if we were thinking about our solar system. But if you were to plot something and you get a decrease as you get towards the more volatile elements, then you're looking at something that's a bit rocky. Whereas if we look at the center, these elements here, these are our hydrophilic elements. So these are our, we call them iron-loving elements. And so if you have an enhancement in these elements, then you're probably looking at material that seems to be core-rich. And if you have a depletion, then you're probably looking at material that is more mantle-rich. So if we look at the first white dwarf in our sample, and we kind of track where these data points are, these are all the data from the white dwarf, You can see that the lithophilic elements, these kind of match solar, but we have a depletion in iron, a small depletion in chromium, and then a really nice constraining upper limit from nickel. And so Andy Buchan has a code called piluted white dwarf, which is a Bayesian framework, and it works out the most likely composition of these accreted bodies. And so his framework came out with that this is actually a mantle-rich fragment of a planetary body that's been accreted onto this white dwarf. So how might that actually happen? So firstly, you have to have some kind of heating that goes on in your system. So maybe internal heating causes your rocky body to melt. And therefore you get your iron and your hydrophilic, so your iron-loving elements migrating down to the core of your body. And so this causes a differentiated body where you have an iron-rich core and an iron-poor mantle, just like we have on the Earth. And then you have to have some kind of collisions, which causes this extreme fragmentation of these bodies so that you end up with bodies that are either really core-rich or really mantle-rich. And then these are the bodies that get perturbed towards the white dwarf and then accreted. And so that's how you can actually study something that is mantle-rich. Because if you had a body that was fragmented and it had the same distribution of core and mantle as something like the Earth, you couldn't tell whether it was differentiated or not. You have to have that mantle-rich fragment. And so this is really letting us actually probe the composition of mantles in exoplanetary systems, which is super exciting, in my opinion. So now I want to show you 3 more white dwarfs in the sample. And so I've grouped these 3 together because they're quite similar. And so if we again look through the data, so the more refractory elements, these all kind of are relatively similar to solar and also bulk Earth. This like orange line here, this is, I've overplotted bulk Earth to kind of guide the eye. But if we actually look at the more volatile elements, so carbon seems to be pretty similar to bulk Earth. But if we actually look at the oxygen abundances for all of these white dwarfs are actually pretty consistent with being solar. And this is a log scale, so it's like an order of magnitude larger than you would expect from bulk Earth. So we think that there's quite a lot of excess oxygen in these systems. And so we do a really, I should say neat trick, maybe it's a bit of a basic trick, to work out what's going on with these systems is we actually do this thing called oxygen budgeting. And so we take our oxygen abundance and we essentially, count the atoms. And so we assign our oxygen to different oxides. So we've got magnesium oxide, silicon dioxide, et cetera, et cetera. And then you assign your oxygen to all of these different oxides, and you want to work out if you've got any oxygen left over. If you have no excess oxygen, then like, good job, you've built yourself like a really nice rocky body. But if you do have excess oxygen, then you have most likely something that could be water rich. That's because we don't think there are other things that could bond with the oxygen. So we think that that's a hint towards a water rich body. And so if we look at the 3 white dwarfs, these are the 3 on the left that I was showing earlier. And these are bar charts just showing how the oxygen was assigned. All 3 of them have excess oxygen. And so we think these 3 white dwarfs could be accreting a body that seems to have water in it. And then this one here, which is quite nice, this is the mantle-rich body. And when we do the oxygen budgeting, we find that within errors, we've just like made a really nice rock. So you've got a nice dry chunk of mantle. So I wanted to put these results into context so that you could actually see basically the abundances of polluted white dwarfs with each other, but also in context of the stars and the solar system material. So this is the last plot I'm going to show you, but I'm going to go through it slowly because it's a lot of information. So on the y-axis, again, we're doing this normalizing to silicon. So we've got iron to silicon ratio. And then on the x-axis, we've got the oxygen to silicon ratio. So in the background, we've got a gray scattered plot, and this is from the Hypatia catalog, and this is of FG stars. So this is giving you an idea of your possible range of initial conditions that you could build planets out of. And then the green and the brown data points, this is data from meteorites in the solar system. And then the orange and the blue data points, ignore the gas versus no gas. There was a bit more of a discussion in the paper about that, but you can ignore that. Essentially, these are all polluted white dwarfs from the literature and some from this paper, showing the abundances that you get for the material that's accreted onto these white dwarfs. And then the red line, this is just showing how the different abundance ratios of the elements in the white dwarf photosphere changes when your elements are sinking out of the photosphere. So essentially, you can like move some of the data points this way, depending on what phase of sinking it's in. So firstly, let's look at, if we look at the x-axis, the oxygen to silicon ratio. So this is helping us to assess whether we actually have something that's oxygen rich and maybe potentially has water. And what you can see is that we have examples of white dwarfs that are accreting things that have stellar levels of oxygen to silicon. And even maybe a little bit more. So these are probably icy bodies, maybe even some Kuiper belt-like bodies. And so these really do have quite a big fraction of potentially water ice in them. You also have bulk earth levels of oxygen, as you can see around here. And then we have one that has an extreme oxygen depletion. We don't understand it. I don't have enough time to talk about it, but I'll happily chat to anyone about that one. And then if we look at the y-axis, we've got the iron to silicon ratio. So this is giving us an idea about whether we've got excess iron or not excess iron, a depletion in iron. And so it's giving you an idea of whether you've got something core rich or mantle rich. And so what you can see here is that you have examples where you've got a lot of iron. So you've got enhanced iron and also depleted iron. And so if we look at this in a whole, we can really see that actually all of these white dwarfs are accreting material that are kind of consistent with range of stellar abundances and also solar system-like abundances. So other than maybe this crazy extreme depletion one, we're not seeing anything that's extremely different to what we see in our own solar system. So just to finish up, I just wanted to say that, yeah, polluted white dwarfs really can act as mass spectrometers to infer the bulk composition of exoplanetary material. I spoke about 4 white dwarfs from my recent papers last year, where we found 1 new white dwarf that's accreting mantle-like material, 3 white dwarfs that seem to be accreting oxygen-rich, potentially water-rich material. And we're really getting to the point that we can study large populations of bulk exoplanetary material. So we can do some statistics. But we're really finding that, you know, things are pretty similar to the solar system, which I think is a really interesting find. So thank you for listening, and I'll happily take any questions.
Thank you, Laura. Question in the back.
Hello. Hello, Laura. That was a nice talk. I am Chandan from Penn State. Can you tell me more about the budgeting of the oxides? Like, did you follow any specific methodology for that?
So, I mean, the mineralogy. We basically just did. You literally take the oxygen and you say, I want this much. I use all of my magnesium to make a magnesium MgO and then Al2O3. We didn't necessarily follow a particular mineralogy, but we do experiment with different forms of some of the oxides, for example, with iron. So iron is a really difficult one. You don't know whether you're in FeO or Fe2O3 or even metallic iron. So we do experiment a little bit with that, but in general, it's very basic. So if you have an idea of doing it in a better way, I'd love to chat.
Thanks, Laura. This is Tim Betting, Sydney University. That was really interesting. How long does it take for this pollution to sink into the white dwarf and be unobservable again?
Yeah, that's a really good question. So it really depends on your white dwarf. So we have what we call DA white dwarfs, which are hydrogen-dominated white dwarfs, and DB white dwarfs, which are helium-dominated white dwarfs. And it's very much dependent on the type of white dwarfs, the temperature, and also your surface gravity. But for some hydrogen-dominated white dwarfs, you can sink out over timescales of days. But for some helium-dominated white dwarfs, you're talking like tens to hundreds of thousands of years. But in terms of the hydrogen ones, it could be observable. We haven't seen it necessarily yet, but it really does range from kind of days to tens of thousands of years.
Just going to take one quick question online.
From online, how do you distinguish between elements inside the white dwarf and debris disks around it?
That is also a really good question. So the kind of neat thing about white dwarfs is they have this, they're so dense that they have a gravitational redshift. And so things that are like inside the white dwarf are offset by at least 30 kilometers a second to what's outside of it. So it's actually relatively easy to distinguish what's going on inside the white dwarf. But there are stuff going on in terms of the debris disks. We don't see that much. There's a few white dwarfs which have circumstellar gas, which show absorption features. But again, because of this gravitational redshift, we can really distinguish between the two. But if you really want to study the dust, then you really need to go to infrared wavelengths, which isn't necessarily where we're looking at to look for the pollution.
Okay, let's thank Laura again.
Thank you.